All right. So now we have the opportunity to review, take a look back at acids and bases. And the reason why this is a good opportunity is because now that we have the ability to understand equilibrium, then we can have a deeper conversation about weak acids or bases. Remember, we said that weak acids, that was the first time we were kind of introduced to equilibrium, right? Because when we have a weak acid, we draw its dissociation with what?
You mean like the double arrows?
That's right. So if I have some generic acid that I say is a weak acid, I draw these double arrows. And again, the dissociation of acids is always the H plus ion and whatever's left with the minus charge, right? A minus. Okay? And now we can have, again, a more deep conversation about these acids because of our understanding of this equilibrium. We're also going to add to our understanding of acids in terms of the relationship between the hydrogen ion and pH. Okay? So let's get into this. The kind of the general idea of acids, or the general name that we call acids, are Brensted acids. And Brensted acid-base reaction is this type of a reaction where a hydrogen ion comes off of an acid. Now, if we include the water in the acid dissociation, then we can identify the water as the Brensted base because it is taking the hydrogen ion. All right. So an acid is a proton or a hydrogen ion donor, whereas the base is the hydrogen ion or proton acceptor. All right. Here's another example: sodium hydroxide and HCl. HCl is our acid. The hydrogen ion is donated to sodium hydroxide to form water, and the hydroxide ion takes the hydrogen ion to form the water, right? So you see that the hydroxide ion received the proton, it's a base. The hydrogen ion, or the HCl, donated the proton, it is the acid. Okay? We call the material that results after a hydrogen ion leaves an acid, we call that the conjugate base. The conjugate base. So, for example, this is our acid. It releases a hydrogen ion. That A minus then is called our conjugate base. Have you heard of these conjugate bases before?
I heard about it in some other science class, I think.
Okay, very good. So the hydrogen ion on its acid, released, and the result is the conjugate base. In a way, if we have this reaction going backwards, this, the conjugate base, actually behaves like a base, accepting a proton, forming the conjugate acid. All right? And we call these conjugate acid-base pairs. So this is the base with its conjugate acid, or you could say this is the acid with its conjugate base. Here's another example. Here's an acid. This is its conjugate base. You see how it differs only by one proton. Here's a base. This is its conjugate acid. It differs, again, only by a hydrogen ion. Okay, so what is the conjugate base of HCl?
The base needs to lose the hydrogen?
That's right.
So Cl, chlorine?
All right, chlorine, but also the chloride ion, right? Because it's an ion.
Oh, yeah.
All right, so what's the conjugate acid of NH3?
The acid, if it's, so would you add a hydrogen ion?
That's right. NH3 has to get a hydrogen ion. And again, that hydrogen ion comes with a positive charge, so it's going to be NH4 plus. Okay, very good. See if you can push pause and fill in these last three squares here. All right. Make sure you did it. Make sure you take your time and exercise. Now, the conjugate base here is going to be this acid without the hydrogen ion. The conjugate acid here is going to be this base with the hydrogen ion, HF, F minus. Very good. Does that make sense?
Yeah, I think I got that.
So we talk about acids and their conjugate bases, or a base and its conjugate acid. All right, so how many of the following are conjugate base pairs? Well, a conjugate base pair is always just one proton. So we see that this one here is a little bit different, isn't it?
Yeah, that one is 2 protons. So 2 of those are conjugate ace pairs.
That's right, 2. This one, these 2 differ by 1 hydrogen, and these 2 differ by 1 hydrogen. Some material is called amphoteric, meaning that it, for example, water, can gain a proton, H3O+, and it can also lose a proton, OH-. Right? So we can think of it as gaining a proton and losing a proton. It depends on the, the direction that you're going. So we should really say plus or minus, plus or minus. There we go. All right, so amphoteric, materials that can gain protons or lose protons. So write a reaction that shows that HCO3- is a Bronsted acid when reacted with the hydroxide ion. All right, can we do this?
We have to write HCO3 as an acid?
That's right, Bronsted acid. So if HCO3- is the acid, and it's reacting with the hydroxide ion, that's going to be the base, what is going to be the product if this acts as an acid?
Well, an acid gives up a proton, right?
That's right.
So it's going to be CO3-.
CO3-?
Yeah.
Well, what happens when you give up a proton?
I don't know.
It's going to be CO3-2-, right? Because it's not just giving up the hydrogen, it's giving up a hydrogen ion with a positive charge. So it's leaving behind that electron. So CO3-2-, and that hydrogen ion is going to go onto the hydroxide ion, and what's it going to form?
That's water.
Very good, H2O. There it is. So if I wanted to draw it in equilibrium, it didn't say anything about that, but that second arrow is what we would include. Okay, very good. Now, what about a reaction base that shows HCO3, a reaction that shows HCO3 behaving like a base, a Bronsted base?
So HCO3- again.
Good, HCO3-. This time it's reacting with H3O+.
And if it's going to behave like a base, it's going to get an electron, a proton. So H2CO3, like that.
Very good, excellent. And what's left behind?
The hydroxide ion?
Well, this is H3O+, and it's going to do what?
Oh, it just loses a proton, so H2O.
That's right, H2O. Very good, excellent. So here we show that HCO3- or the bicarbonate ion is amphoteric. It can take a proton, or it can, it's giving a proton here, or it can take a proton. Excellent. All right, so how many of the following are amphoteric?
You mean it can take and give a proton?
That's right.
Well, I would think H2PO4- can give a proton, give one because it has a hydrogen.
That's true.
HSO4- can give a proton, it has one.
That's true.
H2PO4- can take one because it has a minus charge.
Right.
HC23, the acetic acid, it can give, but I don't think it can get one, can it?
No, it can't. You're not going to add a proton here. You'd have to add a positive charge, and that species is not going to occur. This is just a weak acid with its proton. What about this one? Can this one take a proton?
I think so, because it's HSO4-, so it has room for another proton.
Now, this is kind of a tricky question here because there's something about HSO4. If I give it a proton, it makes H2SO4. Does that look familiar?
Well, I don't know. What do you mean?
That's a special kind of acid. We have 7 special acids that we have a separate category for.
Oh, a strong acid?
That's right. It's a strong acid. And when strong acids are in water, they'll never be able to take a proton. So for example, Cl-, you can't have the chloride ion behave like a base and remove a hydrogen ion from water. And the reason this doesn't happen is because that is the conjugate base of a strong acid. So because HSO4 minus is the conjugate base of a strong acid, it means it can't take that extra proton. All right. So in here we just have the one. We just have the H2PO4 minus that can both take and give a proton. All right. So the hydronium ion is the strongest acid in an aqueous solution, H+. And the hydroxide ion is the strongest possible base in an aqueous solution. Stronger bases react completely to give just the hydroxide ion. Stronger acids also react completely to just give the hydrogen ion. So the reaction of all stronger acids and bases in water to the same strength is termed leveling. All right. So if we have an acid-base reaction that occurs in favor of, or acid-base reactions, they'll occur in favor of the weaker acid and base. So what does that mean? Well, if you think about this scale, in this scale we have the strongest acids here at the top of this red arrow and weaker acids down on the bottom. You see any strong acids in there?
Yeah, I see HCl and HNO3. Oh, and HClO4.
That's right. Should we make a list of our strong acids? Make sure we remember those.
Sure.
HCl. What else?
HBr and HI.
Very good. HBr and HI. And then the oxy ones?
HClO4, HClO3, and HCl, let's see, H2SO4 and HNO3.
Okay, very good. Those are our 7 strong acids: hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, and sulfuric acid. So we see 3 of our strong acids up here. If this acid is very strong, let's say HClO4, which it says it is here, then what that essentially is also saying is that its conjugate base is very weak. ClO4 minus cannot interact with water to take a hydrogen ion and leave behind the hydroxide ion. All right. Down here is a very weak acid. NH3 is not a good acid. So therefore, that must mean that its conjugate base, NH2, is a very strong base. All right. So because if NH2 minus existed in solution and it was interacting with water, it would want to form NH3 and release the hydroxide ion. All right. And we know that because this is not a good acid. It doesn't want to release that hydrogen and form NH2 minus. So if it's going to have to, if NH2 minus is in solution, it's going to be a very strong base. So the conjugate base pairs are reciprocal in their strength. Strong acid, very weak conjugate base. Strong, or weak acid, very strong conjugate base. Okay. So, identify the preferred direction of this reaction. Here's H3O plus combining with CO3 minus to form HCO3 minus and water. Okay? So the hydronium ion is a very strong base. Water is therefore not a very strong, this hydronium ion is a very strong acid. Therefore, water is not a very strong base. Do you see that?
Yeah, I see that.
HCO3 minus, or CO3 minus, right here, here's H2CO3 minus, is a relatively strong acid. So CO3 minus is not as strong of a base compared to HC2O3 minus's acid strength. So the preferred direction here is going to be, whoops, to the right, because this is the stronger acid, and it's going to want to create the going to want to create the weaker acid here. All right, NH4 plus, HCO3 minus, right? NH3 and H2CO3. H2CO3, it's on this list in terms of strength of acids. NH4 plus is a weaker acid. Going to the right here, we're asking NH4 plus to give that hydrogen to HCO3 minus. If you go from the left, we're asking, who are we asking to be the acid? If we go product side to this side, which one of these is behaving like the Bronsted acid?
The H2CO3, because it is it's giving up a proton.
Very good. This is behaving like an acid. Going to the right, this is behaving like the acid, and going to the left, this is behaving like the acid. Because this is the stronger acid, then this reaction is going to want to proceed to the left, because this acid is stronger than NH4 plus. How about this? Who wants which way is this reaction going to proceed? Who are we asking to behave like the acid on the left?
HCN.
And who are we asking to behave like the acid on the right?
HCl.
What's stronger, HCN or HCl?
I don't see HCl on the list, but I know it's HCl because it's a strong acid.
That's right. HCl is essentially H3O plus because it is already going to be dissociated when it's in water. So this will move to the left as well. So again, we look and see who's behaving as the acid. We look and see which one of the acids is stronger, and that is where the equilibrium will lie, towards that side of the reaction. Which reaction is not written as its preferred direction from left to right? All right. I'll let you guys examine this one. Take your time, push pause, and then come back and give a good answer. Okay, did you get to take a look?
Well, A, you have the HC2H3O2, the acetic acid, behaving as the acid, right?
That's right.
And on the right there, you have the ASO4, that one?
Yeah, that's right. Arsenate ion, or arsenic acid, arsenate ion.
Arsenic acid behaving as the acid. And it says that that one is stronger than the acetic acid, so that one goes to the left. And that's not the direction that we have it written.
Okay. How about this one?
That one, you have the arsenic heading to the right, and you have the other one. What is that one called?
That's the arsenate.
Arsenate heading to the left. And that one is in the preferred direction because the arsenic is stronger.
All right. We know that they're not all preferred, so that looks like it's going to be the answer, right? Oh, we're looking for the one that's not written in the preferred direction.
Yeah, you went too fast.
Oh, sorry about that. Let's look at C then.
This is acetic acid, and it is weaker than the H3, or it's stronger, so it is in the right direction.
Okay, very good. And then this would be all are in the right direction. All right, good. Now, let's look at, okay, this is a good place to stop, actually. We'll see.